In section 1.7, we're going to talk about inequalities. Four inequalities that we're going to talk about are linear inequalities, three-part inequalities, quadratic inequalities, and rational inequalities. In the next section, we will talk about absolute value inequalities. We're going to go through these four examples. We will be using a lot of interval notation, and if you need a refresher on interval notation, page 151 of the book talks about set notation and interval notation, and we're going to use that in each of these examples anyway. So first, let's take a look at this linear inequality. Negative 3x plus 6 less than or equal to 2x plus 1. We're going to solve. And we are going to give the solution using interval notation. So just like with an equation, let's isolate x. And this statement says 1 is less than or equal to x. Now, let's take a look at a number line first. I prefer shading a number line and then going to the interval notation. We want to communicate that one is less than or equal to x. And this is the same as saying x is greater than or equal to 1. I personally prefer to look at that statement. So if we wanted to say x is greater than or equal to 1, let's just plot 0, plot 1 on the number line. And what I do, mostly for the sake of the student, is I'm going to put a bracket if needed, a parentheses if needed, facing the shaded direction. But quite commonly on a number line, you will see a filled in dot to signify set inclusion. And if we did not have set inclusion, so if this were a strictly greater than, x strictly greater than 1, we would use a parentheses, which would be the same as an open dot. We'll see that in an upcoming example. So if I write it like this, it's easier for me to see that the solution in interval notation is bracket 1, and then we've got the shading, all the way to positive infinity, and we always have a parentheses next to plus or minus infinity. We can never actually include positive or negative infinity in the set, so to communicate that, we will always have a parentheses next to plus or minus infinity. Okay, this is going to be a three-part inequality. The previous example and this example we will see again in the next section when we do absolute value inequalities. We will end up solving inequalities that are quite similar to example 1 and example 2 here. Okay, so this is a three-part inequality, and the goal is to isolate x in the middle. So I can subtract 4 to start. Divide everything by 5. And when you have a three-part inequality, do try to keep the statement written from left to right, just like we speak English. So we're going to want the least value over here, x in the middle, and then the greatest value. So if you had had to multiply by a negative somewhere, you would flip the inequality signs, take the opposite of the inequality sign, and you could end up with a statement that reads right to left. The reason I mention that is because we don't want to confuse that going to the number line and accidentally write the greater value closer to negative infinity, you know, if we were to accidentally switch these around. So x is in the middle. I'm going to shade from negative 14 over 5 to negative 2 over 5, and again, so it's clear for the student to see when I'm lecturing, I put parentheses on the number line rather than a open circle because it may not be super clear, especially if we were in class and I were on the whiteboard and a student were sitting in the back. It might be kind of hard to tell if that's a filled in dot or an open dot, so I always just use parentheses or brackets depending on which is necessary. And in this case, interval notation, when we don't have set inclusion of the value, we use parentheses. So this strictly less than is the reason why we're going to have parentheses in our interval notation. And again, I do the number line first because then it helps me see how to write that in interval notation. Parentheses, negative 14 over 5, all of the shading, and then negative 2/5, and then close the parentheses. And this is an interval, so real quick, context is important in all forms of communication. If you saw this exactly with no context, it could be confused for an ordered pair. This is the interval notation that says x is strictly between negative 14 over 5 and negative 2 over 5, and we know that because of the context of the problem. So if we were graphing lines or something like that, and we saw this on the paper, we would say, okay, that's the ordered pair. So make sure that you communicate thoroughly, and you know, things like that in mathematics don't tend to be an issue. In a previous section, we solved quadratic equations. And now we're going to solve quadratic inequalities. And quadratic inequalities, we want to get into this form. The first thing we're going to do with this quadratic inequality is find what we call critical values. We're going to do that by solving the corresponding quadratic equation. So whether we start with a strictly less than or a less than or equal to, the corresponding QE quadratic equation is ax squared plus bx plus c equals 0. So when we find the two solutions to the corresponding quadratic equation, and here I'm picking a generic K1 and K2, those are called the critical values. So those are not the solutions to the inequality. The inequality is going to have an interval that, or multiple intervals that solve the inequality. We are finding the critical values first, and then we are separating the number line CVs is short for critical values. So then we're going to separate the number line at the critical values. And once we've done that, we can identify and test each interval and that will allow us to determine if the interval solves the inequality. So let's take a look at an example. Let's say we have x minus 5 times 2x plus 3 strictly greater than 0. And this example is kind of nice because we're not going to spend the time factoring out a quadratic. We'll just start with that. If you need more work on factoring quadratics, we can go back a couple sections and do that. But in this section we are learning how to solve the inequality. So on this example in particular, we just already have a factored form of a quadratic equation that needs to be an equals sign. And the solutions to the corresponding quadratic equation are 5 that comes from this factor and negative 3/2 that come from this factor, and we call these critical values. That is important. If you're like me, you like a visual, so I separate the number line, I draw a number line and then separate it at the critical value. And then I'm going to label the intervals. This interval over here is negative infinity to negative 3/2, and we are not going to include negative 3/2. The middle interval is negative 3/2 to 5, not inclusive because of the strictly greater than. And the interval over here is 5 to infinity. So all we need to do is pick a test value from each interval, test that in the original inequality, and that'll determine if that interval is part of the solution, it is important to note that critical values cannot be test values. So a test value is valid if it is strictly inside the interval, regardless of whether or not this is a strictly greater than or less than, or a greater than or equal to, less than or equal to. Always have to pick a test value strictly inside that interval. So in negative infinity to negative 3/2. And the reason why I can pick any test value is because any value inside that interval represents that entire interval. We are going to get a true statement according to the original, or a false statement according to the original. And if I choose negative 10, which is strictly inside this interval, it will give me a statement of true or false, and that represents every real number strictly inside that interval, which is different than if we were solving just a quadratic equation. We would have two solutions for a quadratic. So if I test x equals negative 10, negative 10 minus 5 times 2 times negative 10 plus 3, is that greater than 0? And if we simplify that, I'm out of room on the page, we do get a true statement. This is a true statement, and that tells us that negative infinity to negative 3/2 is in the solution. I'm going to move this up a little bit. Let's test the middle interval. So how about, I always like to use the test value of 0 if at all possible. And 0 is a valid test value in negative 3/2 to 5. So in the original, we'd have 0 minus 5, 2 times 0 plus 3, and is that greater than 0? So we're going to end up with negative 15 greater than 0, which is a false statement. And the conclusion from that is the interval negative 3/2 to 5 is not in the solution. One more interval to test. So maybe I test x equals 7. And this is for the interval 5 to infinity. So I'm going to substitute 7 back into the original inequality and see if we get a true statement. This does give us a true statement, so we'll have a positive number from here. So 2 times 17 greater than 0, 34 is greater than 0, and that tells us that 5 to infinity is in the solution set. So now we just need to write our answer, and we will need to use set union. Set union translates to or in English. So in this interval notation, this says x is strictly inside the interval negative infinity to negative 3/2, or x is strictly inside the interval 5 to infinity. And if we wanted to show that, all we have to do is backtrack. This came from all of our work. If we pick any value strictly inside this interval, it makes the original a true statement. And when we say, solve in mathematics, that's what we're looking to do. Find values that make the statement true. That's what solve the problem is. So if we pick any value from 5 to infinity, substitute that into the original, we get a true statement. However, any value strictly between negative 3/2 and 5 will not give us a true statement, so we need to use set union to union those two different intervals together. And a big takeaway from quadratic inequalities is that's the first time we've seen critical values, and in rational inequalities we will also use critical values. So the first question is, how do we get critical values for rational inequalities? So a rational inequality is going to be a over b less than or greater than a over b less than or equal to, greater than or equal to, and then we want 0 on the other side. So whatever this rational expression might be, this a over b, any real number k that solves the numerator equal to 0, and any real number that solves b equals 0 is a critical value. Quick side note, no matter, even if it's greater than or equal to 0 or less than or equal to 0, the solution to the denominator set equal to 0 cannot be included. So we're always going to be using a parentheses in the interval notation next to the value that solves denominator equal to 0. If we use set inclusion, so close brackets, for any x values that were critical values coming from the denominator set equal to 0, we would actually be saying we're dividing by 0, and of course that's division by 0 is undefined. So after that, so the difference between the process and the quadratic inequality that we looked at and this rational inequality is only where the critical values come from. After we find the critical values, the process is the same as the previous example. So we're going to find the critical values, and then we're going to proceed with testing the intervals and giving the solution. So let's take a look at an example. Now we want we want the rational inequality to have a 0 on one side and a single rational expression on the other. So if you have to do some arithmetic and adding and subtracting to get 0 on one side, finding a common denominator, that's kind of some upfront work, some elementary algebra type work. So for the sake of this lecture, this example that I'm covering, we've already got that taken care of. So we have a single rational expression less than or equal to 0. So again, if you are given the rational inequality and you don't have 0 on one side, you need to algebraically manipulate the inequality to get 0 on one side. And if you had two rational expressions over here, you would need to find a common denominator, make it a single rational expression, then move forward with finding critical values. So we are able to jump right into finding the CVs, and that comes from x minus 8 equals 0. So x equals 8 is a CV, and then x plus 6 equals 0, that is setting the denominator equal to 0. So x equals negative 6 is a CV, and then note negative 6 cannot be included in the interval solution because that would cause division by 0. So we have a less than or equal to, which the CV of 8 will require a square bracket, an inclusive, but the CV of negative 6, no matter what the outcome, we'll have to use a parentheses next to that in the interval notation. So the interval on the left is negative infinity to negative 6. I just like to label them. And so I've got a parentheses next to the negative 6, a parentheses next to the negative 6. X equals 8 is a CV from the numerator. So if I went back and 8 minus 8 less than or equal to 0, there's nothing wrong with that. That doesn't cause division by 0. So since that is a less than or equal to, we've got the inclusive square bracket. And right here, this interval is 8 to infinity. Again, we are allowed to include 8. We are not allowed to include negative 6. So let's test. How about x equals negative 7 right there? I like testing x equals 0 if at all possible. And how about x equals 11 over here? So negative 7 minus 8 over negative 7 plus 6. Is this less than or equal to 0? This is going to be a positive number. So negative 15 over negative 1, which is 15 less than 0, which is false. So that interval, negative infinity to negative 6, is not included in the solution. And if we did the test point x equals 0, we do have a negative value on this side. A negative value is less than or equal to 0, so that is true. That interval will be included in the solution. Over here I chose 11 as a test point, so 11 minus 8 over 11 plus 6. That is going to be a positive number. A positive number is not less than or equal to 0, so bracket 8 to infinity is not part of the solution. Now we've tested it, we've taken care of all the intervals, we write our answer. The solution is simply the interval that solves the original inequality. In this case, we do not need set union. parentheses -6, comma 8, bracket. And if you went back, you could pick any value between -6 up to and including 8, and it would solve this original inequality.